Hello and welcome to the 8th video in the Introduction to our Workshop series accompanying videos. This is a group of a set of videos to go along with the workshops run by the QIMR Berghofer Statistics Unit on one of the many services we do. Today we'll be looking at just some basic analysis. We will be using one of the data sets we've looked at previously, which is WK1_9_10_WK3_16_pulse_data_txt.csv. That was a mouthful. Anyway, we'll be using that data set. So hopefully you have that data when you got the rest of the material. Hopefully also you've done the previous sections or at least have some other experience in R if you wanted to follow along. So we've got a basic analysis section, so we're not doing too much in-depth analysis or very advanced techniques. We're just going to do some basic analysis, and this video is going to be basic categorical analysis. So categorical analysis, really briefly, is rather than modeling continuous outcomes, we're looking at those variables that are in categories or factors or levels, and the types of basic analysis we get with them. So it's going to be mostly in R. We're not really going to talk about the statistical theory behind these tests or too much about the statistics. It's just really going to be showing how we do them. So if you do want to follow along, make sure you know where that data set is saved. So you can set your working directory to that place, you have to call the data in, and then we can follow along. So we'll jump across here. Okay, so I'm reading in the data set using the read.csv function, and I'm going to call it pulse_data like we have before. So pulse data comes in 110 observations of 12 variables. If I look at it, I've seen this before, different students with some different variables, pulses before and after they did some exercise, the type of exercise they did, a few other variables there. So the first test we're going to look at is the chi-square test. So the chi-square test is when we've got two categorical outcomes, so two outcomes that have levels or categories, and we're going to look if there's an association between the two. So in this case here, we're going to look to see if there's an association between gender and smoking status. So if we look back at the data, we have a gender variable and we have a smokes variable. So we want to see if there is an association, say if one gender is more likely to smoke than another. For that we use the chi-square test. And the function to do that is this function here. So chisq.test for chi-square test. And our inputs to that are going to be the two variables we're interested in. So we've got pulse data $gender, so that's going to be the vector that contains all the values for gender. And we've got pulse data $smokes, so that's the vector that contains all the values for smokes. Because they both come from the same data set or data frame object in this case, we know that the values at each position in the vector for both those vectors match up with each other. We've also got this extra input here for correct equals false, and I'll talk a bit about that later. So to begin with, I'm just going to highlight this function and all its inputs. So this is just so that's the chi-square.test function. Chi-square.test function. Two inputs are the two vectors of interest, with that correct equals false there. If I just control enter on that line of code, this is the output I get. It's telling me that I've done a Pearson's chi-squared test. It's giving me the chi-squared value, the degrees of freedom, and the p-value. It's telling me what data I've done my test on. It's literally just telling me exactly what I told it, pulse data $gender and pulse data $smokes. So that I know exactly where this information has come from. And it's giving me this brief information. And realistically, to do a chi-square test, that is the most important points there. It's giving me the p-value, degrees of freedom, the value. but there's a lot more that R is doing in that function, and that function does for us, that I might want to use. And so the way to access it most easily is going to be to save it as an object, like I'm doing here with my assigning. So what I want to do is I want to take the output of the chi-square test function. I'm going to save it as this object called chi-pulse data. So if I just leave my cursor there on that line, Control Enter, you can see here now that this chi-pulse data object has appeared in my environment, saying it's a list of 9. If I hit this drop-down arrow here, I can see all the things inside this object. So we've talked about lists in previous videos, how a list is just a collection of elements, and those elements can be anything. That's how a lot of test and model output is stored, because it's an object that contains all different kinds of information, and those different kinds of information can be different from each other. So it's here we've got a statistic, we've got a parameter, we've got a p-value, a method, data, and lots of other things. If I wasn't looking at the environment and say I just wanted to enter it here in the console, it still gives me just that. So that's one thing to note, that while the output, I can save it and see that it exists there, just by calling the object output itself won't necessarily give me anything more. So the way to find out what else is in there is either be to look at the environment or just start accessing things out of there. How to know what's in the object you've saved from a model output is either looking up the documentation. So over here, I could look up chi-square test, and after arguments, it'll give me the values that comes out, statistic, parameter, p-value, method, etc. And the way to access these things is with the $, just like with the data frame. So one of the things I can access out of the chi-square test output is the observed output. And that's just essentially a table of the 2 vectors. So same thing we've talked about the table function in previous videos. That gives you what was observed, the combination. So that was 48 females who did not smoke and 3 females who did, 51 males who didn't, and 8 males who did. So that was the observed numbers. And we can also extract the expected numbers as well. So this is based on the marginal probabilities, what we would have expected to see if there's absolutely no association. I acknowledge that I'm going fairly quickly through this. This is what these videos are designed to be. They're designed to be complementary. So you can pause and take your time and go through the booklet again. So I do apologize if you feel I'm going fast. Please do just check the book if you feel that's the case. Anyway, so now that we've seen these observed and expected, and especially the expected, looking at the expected is a very important thing to do, because one of the goodest things you have to check for the chi-square test is that the expected count less than 5 rule or guideline. You need to make sure that there's not too many of your expected cell counts less than 5. Otherwise, the Pearson chi-square test isn't appropriate, which is why it's really good to save the output and then check it with the expected element from the output. Is a good reason to do that. There are many more things you can get from the output from the chi-square test, so I'll leave it up to you guys to check the documentation of the chi-square test, like you should do with any new function you're using, and get to understand things there. Some other things while we're here is often when you're reporting a chi-square test and you've done some analysis looking for associations between 2 variables, you might want to report some of the proportions or the number and percentages between between the categorical variables. So a quick way to do that just while we're here is with a couple of different functions. So we've talked about the table before and how the table essentially just categorizes each combination of the categorical variables. So the table function just does that, like I've seen before with the observed. If we wanted to get conditional proportions, or sorry, marginal proportions, so the proportion of how many females are no or yes, or the proportion of how many no's are female or male, we can use this function prop table. So prop table works on a table input, which is why I've got it here inside the brackets for prop table. So there's the output of this table function is going to go inside as an argument to prop table. So prop table here is going to calculate the column proportions, because I've got 2 here, meaning it's going to go through columns rather than rows. So that output there has told me the proportion of no's, that is female, is 48%, and the proportion of females, getting mixed up. The proportion of no's that are female is 48% roughly, and the proportion of no's that is male is a little over 51%. The proportion of yeses that is female is 27%, and the proportion of males that is yeses that is males is 72%. Carefully don't mix those up. So prop table will give you those column or row percentages. 2 here means column. If we change that to a 1, it would be rows. And then to make this easier, what I've done here as well is I've put that output into the round function, which we've talked about in one of our very early videos. And I've got a 2 here as the second argument, which will round all those numbers to 2 decimal places. So basically, if you are looking, say in this fictional example, to look at the association between gender and smoking, these are the 2 things you'd do. You'd get your proportion, marginal proportions, and then you'd do your chi-square test. Now, earlier I did use that extra input of correct equals false. Back up here, there was this extra input of correct, and I made that equal false. This is an important thing to do to make sure you are performing the test that you're expecting to perform. One of the things this chi-square test function does is it will use some different defaults in different versions of the chi-square test that different people believe are sometimes better or not. And so the variation it often does by default is called the Yates correction. It won't always necessarily do this, but it can do this sometimes if you're not aware of it. So if you want to make sure that it's always doing exactly the Pearson chi-square test, add that correct equals false, because if I say just highlight this output here, this code here, it tells me that it's doing the Pearson's chi-square test with Yates continuity correction. And I won't go into Yates continuity correction or why you should or shouldn't use it. I'm just letting you know that sometimes with the chi-square test function, we'll do that by default. So if you want to make sure that's not happening so that you know exactly what method is being done, add this correct equals false argument in. Okay. So just before I talked about how if the expected counts, if there was too many expected counts less than 5, so if more than 20% of the cases with expected counts are less than 5, we can't use Pearson's chi-square test. So the alternative to the chi-square test, when we've got those very low numbers, is called Fisher's exact test. So what I want to do here is I'm going to make this fake data table. Don't worry too much about how I'm making this. It's not super important here, but I have left the code here of how I've made it in case people are interested in trying out how to do it themselves and a little bit extra. But essentially, I've got this table here that's going to be helping us look at the fictional in the sense that this data is made up, relationship between high or low salt intake and high or low systolic blood pressure. Now, if I were to do a chi-square test on this table, now, really quick while I'm here as well, previously for the chi-square test, we used an x and a y variable, so two vector inputs for that function. If you have the data already in a table form where each cell is a combination of a row and a column, the chi-square test works as well, which is what I'm doing here. So basically what this line of code is doing is it's doing the chi-square test on this fake data and extracting the expected out straight away. So these are the expecteds. There's an expected of 4 and expected of 2, and it has given me this warning message saying chi-square approximation may be incorrect, because it can also pick up that there are very low numbers there as well. So when this happens, what we do next is the Fisher's exact test, and the function for this is fisher.test. Now, the chi-square test can take either 2 vectors as the argument input, or it can take a table format. The Fisher test function definitely needs a table format, just as one of the differences that's good to be aware of. So either if you have your 2 vectors in your data set that you want to use Fisher's exact test on, the thing to do is to use the table function on those 2 vectors and either put that output straight into the Fisher's.test or save that output as an object and use that object inside the Fisher.test like I'm doing here with mock table. But highlighting this line of code and running that function gives me this p-value of 0.6. So not significant, but that's how I would run a Fisher exact test. Another thing we'll talk about while we're here is for paired categorical data. There's the Mcnamar's test. So we're going to make some paired data, our pulse data set. I'm going to basically categorize the 2 pulse variables. So there's the pulse taken before exercise and the pulse taken afterwards. And then using the cut function that we've talked about in previous videos, I'm going to split the the 2 variables up into less than 80 and greater than 80. Run those there. If I use just table on a single vector, I can see how many are in each category. So less than 80 has 44 in pulse 2, and 80 and above has 55. Then in pulse 1, less than 80 is 71, and 80 and above is 38. If I do a table on those 2 to see the how the 2 are related, the distribution between the different categories, I can see 38 is less than 80 in both pulses. 6 people are less than 80 in the second one, but greater than 80 in the first one. Remember, the first vector that goes in gives you your rows. That can be confusing if this is the output it gives you. But the reason it's good to do a table is because the Mcnamar test needs a table as an input, like the Fisher's exact test. So here we've got Mcnamar test, very similar to Fisher's test in terms of the function name. So Mcnamar test, I've got the table in here, turning my 2 variables that I want to find the association between into a table. Now I could save that table output as an object and then put it in here, or I can just put it straight in there like it is now. It's really up to you, whichever way you want to do it. I've also got the correct equals false here. That's just a good thing. And of course, anytime you do this, it's good to be aware of the test, what the test is doing, and the defaults that might be happening. So it's always good to check the documentation. I'm just running through this very quickly because that's what these videos are designed to be. But if I run that line of code, this is what I get. It's telling me what type of test I ran, the data that I used, the Mcnamar's chi-squared value, degrees of freedom, and the p-value. It's very significant, so it suggests that there is a relationship between your pulse and whether it's before or after exercise, saying that one is, it's likely to be higher for the second one in this case. If I don't use the correct equals false, it's going to put a continuity correction in. A lot of the R functions by default will try and put the continuity correction in if it thinks it needs it. You can see here that it has somewhat changed the chi-square value and the p-value. So it's good to be aware that a lot of the R functions will try and do a continuity correction by default. So it's good to check the documentation for that function first to see if there is something that controls that, or if there's a possibility for continuity correction and how you can stop it, or allow it if you want. If you are aware of what the continuity correction is and you want to allow it, that's completely up to you. But if you're not sure what that is, go talk to a statistician to see if you should be using it. But it's always good just to check those things. Okay. Well, that's it for this video. Just on the basic analysis for some categorical variable analysis. Remember to try the examples and other activities in the book, because there's a few more there. And come to the workshops, do the rest of the book, and remember the best way to do R is by, sorry, the best way to learn R is by doing R.